In this clip, we'll work through where the Cobb-Douglas production function comes from. And so we're actually going to solve that partial differential equation. This will be the only time we solve a PDE in the entire course. So suppose that the data suggest that when labor and capital both vanish, so in other words, go to zero, production also goes to zero. Suppose they also determine that the marginal productivity of labor is proportional to the amount of production per labor. So let's start turning this a little bit into mathematics here. So the marginal productivity of labor, what does that mean? Well, that's the amount by which productivity increases with labor, or the rate of change of productivity with respect to labor, or the rate of change of productivity with respect to labor. So it's a partial derivative. And then we have is proportional to, so that means equals a constant of proportionality times. And then we have the amount of production per labor. So that's the amount of production per the amount of labor. There we go. Okay, so we have one equation already, and then we go on to number 3, our third point, which says that the marginal productivity of capital, so marginal productivity of capital, that's the amount by which, or the rate at which production increases with a change in capital, again, is proportional to, so we'll take some other symbol for our constant this time because it could be a different constant of proportionality. And then we have the amount of production per capital. And so that's going to be production per, oh, I wrote C for capital. I meant K. Sorry. Let me be consistent there. There we go. Okay, so then that's our second equation, equation number 2. All right. And then the last one says that if labor or capital increases by a factor m, production also increases by the same factor. So if m were 2, we'd be saying if you double your labor, you double your production, or if you double your capital, you double your production. Okay, so those are the assumptions that we're making here, and they sound more or less fairly reasonable. So now we introduce something unreasonable. We look for a solution of the form, let's take PLK to be a function which only depends on L multiplied by a function which only depends on K. Now, like I said, there's no justification for doing this. But when you're solving a differential equation, it's okay to make an unfounded assumption if it allows you to cough up a solution, because at the end of the day, when you're there holding a solution and you can verify that it is a solution, like we did in the last couple clips, then who cares how you got it? If you cheated, so you cheated. You still win. It doesn't invalidate your solution. So okay, so this particular thing where we have all the L's over here and all the K's over here and never the twain shall meet, this is called separation of variables, and it turns out to be a remarkably successful technique for solving PDEs. Okay, so let's see. So by our first equation, let's see. The first one says that if we differentiate P with respect to L, okay, so if we differentiate with respect to L, our function P that we're assuming right here, this should give us alpha times P over L. All right, and P, remember, is F times G. So let's see. So when we do this derivative on the left-hand side, it completely ignores the G. So we end up with the partial of F with respect to L times G on the left, and then on the right side we have alpha times F times G over L. And now let's see, we've got g on both sides, so we'll just cancel that guy off. And then I'm going to do something crazy, and I'm going to multiply the dl to the other side and divide the f to the other side. So these guys are going to change places. So it looks like df over f is equal to alpha dl over L. And you might say, hey, that's crackpot nonsense. There's no justification for splitting a symbol in half and treating it like those two things are actually reasonable expressions you can work with. And you'd be totally justified in that criticism. This is actually a mnemonic device, and it can be justified using a change of variables. Again, we're not going to do that here. If you want to take a differential equations course, we'll do it in detail right there. But for now, just take it as it is and assume that we can just brazenly integrate both sides with no regard to our own self-preservation. And what do we have? So on the left, we're going to get a log of f, and I guess in absolute values. And on the right side, we're going to get alpha times log of L and some constant. And so if I exponentiate both sides, then I'm going to get that f as a function of L looks like some other constants, call it C1 times L to the alpha, using log rules. Okay. And then similarly, it's basically the exact same computation. The second equation gives that g looks like some other constant times k to the beta. Okay. So since the function we're looking for is the product of f and g, it must look like some constant c1, c2 times L to the alpha, k to the beta. And now if we look at the first condition that we're assuming, we can see that alpha has to be positive and beta has to be positive, because otherwise this function would become unbounded as L or k tends to 0. And I guess the last thing to do is to see what we have from the fourth, if I can remember how to do Roman numeral 4, the fourth criteria. So let's see. So if we do, if we double or m tuple our labor, and we double or m tuple our capital, then this should result in the being m times our original function, right? So let's see what we have. So from our formula, we've got that this is going to be some constant times, and now we've got ml to the alpha, mk to the beta, and so this is m to the alpha plus beta, pulling it out, L alpha k beta. But this is supposed to be, so this equation right here comes by our assumption 4. This is supposed to be m times the original function. Oops. And so from this, we compare and go, oh, this guy and this guy have to be the same. So that implies alpha plus beta is equal to 1, or alpha, beta equals 1 minus alpha. So putting this all together, and I think also I'm going to ditch this thing right here and just refer to it from now on as the single constant b, because what is it? It's some constant. Then that gives us our formula as we saw from a couple lessons back. And so again, I don't expect you to be able to solve a differential equation like this. I just wanted to show you an example of how it's done and to see how we can go from, 4 fairly easy to derive assumptions, 4 things that are observations you could make about data, and then write those observations down as equations like we did with our equations 1 and 2, and then use those equations to actually produce a formula. So we went from ideas to a mathematical formula that expresses the law governing the system. Pretty cool.